After we did our experiment, we put all of our data into an Excel file, and we have different tabs for the different substances that we used. And for example, this is our tab for water. On the table to the left, you'll find all of our data that we needed to find the rate of flow of water. We did 5 different trials, and the times for each trial is listed in the middle column, and then the rate per second is listed in the column to the right. And so our average rate was 0.04 cups per second, which we needed for the experimental part. In the table to the right, we have all of our data that we got after we did the actual experiment. We did 5 tests, and we started with 1 cup of water already in the measuring cup because there was already some snow on the ground in the original problem. So for this situation, we started with 1 cup and we wanted to increase it to 2 and see how many seconds that would take. Our average was about 29 seconds, and we took these times and used our original rate of flow to kind of calculate how many cups we should have gotten to see if our experimental and mathematical data matched up. Here's an overview of the process that we used.
Remember, with our original data, we got that it took about 27 seconds to fill up a cup of water from 0 to 1 cups. For the second part of our experiment, we are going to figure out how long it took to fill the cup from 1 cup of water to 2 cups, because in the problem there was already snow on the ground. This is the number that we want to look for to make sure that our experimental and our mathematical numbers match. And whenever we actually did the experiment, we did 5 tests, and our times for each of those were 26, 29 seconds, 29, 27, and 31 seconds, which that all averages out to about 29 seconds. So right away we can go ahead and see that our average was 29 seconds, which was 2 more seconds than our original time, but in account for rounding errors, that might be okay. To figure out how many cups we should have gotten with these times and the original rate of flow, we're going to put them into a formula. We're going to use y equals mx plus b, where y equals the number of cups that we should have gotten at the end of that amount of time. M equals our original rate of flow, which in this case is 0.04 cups per second. X equals whatever time we got for this experiment. So we're going to use each of these 5 numbers over here. For this, for example, we're going to use 26 seconds. And finally, B is our initial starting point, which in this case is 1 cup, because we started with 1 cup of water. When we plug in our values, we get that y equals 0.04 times 26 plus 1, which, rounding to the nearest significant digit, is about 2 cups of water. So, this is saying that our experimental data and our mathematical data lined up. Although this said 29 seconds was the average to fill it from 1 to 2, and 27 seconds was the average to fill it from 0 to 1, with rounding errors in and all, mathematically we should have gotten 2 cups. So that's awesome. And we did this for all of the other trials, and we took the average at the end, and the average for water did end up being 2 cups, both experimentally and mathematically.
So again, we followed that same procedure for each of the tests, and our average in the end was 2 cups, which is what we should have gotten, which does tell us that our experimental data and our mathematical data lined up. For the white vinegar, we did the same process. Here on the left-hand column table, we have our data for finding the rate of flow, which our average for that was also 0.04 seconds, which is the same as water. Except we didn't have as much white vinegar as we did water, so instead of starting with 1 cup and increasing to 2, we started with half a cup and just increased it to 1.5 cups. So again, our table to the right is our experimental data, and we plugged all those different times into the y equals mx plus b formula, again to see if our experimental and mathematical data matched. And at the end, what we should have gotten is 1.5 cups, and that's what we did get. So the white vinegar was also mathematically accurate. This is our tab for cheerwine, which is a kind of soda. For cheerwine, the average rate of flow was about 0.03 cups per second, which is a little bit different than the white vinegar and the water. But again, we followed the same process. And same as the white vinegar, we didn't have enough cheerwine kind of to go around, so we started at half a cup and increased it to 1 cup. So that's why over here, the average time is 30 seconds, and over here it's 14. On the table to the left, that's whenever we were timing for 0 to 1, and on the table to the right, that's when we were timing from half to 1. So it should be about half time, so that's good. And in the end, we should have gotten 1 cup, and that was our average. So again, mathematically and experimentally, they line up. This is our tab for vegetable oil. The vegetable oil had a rate of flow of 0.02 cups per second, or about 45 seconds for a cup. After we did the experiment, we determined that it took about 44 seconds to fill it up from 1 cup to 2 cups. And whenever we plugged all that data into our y equals mx plus b formula, we got that we should have gotten 2 cups at those times. So again, mathematical and experimentally, they match. And finally, sugar. Sugar was a little bit different. We had a rate of flow of 0.08 cups per second of the sugar. And that was about 13 seconds per cup, which is a lot faster than any of the other ones that we had done. But again, whenever we did the experiment and we recorded all of our data, we started with 1 cup and increased to 2. And it does turn out that with our experimental times, we should have gotten 2 cups, which again, experimentally and mathematically match. And again, for the sugar, we did not use aluminum foil at the end of the funnel because at first we tried and the holes were just too small, the sugar wouldn't fall through very well. So this is the only test which we actually took the foil off and just used the funnel as is. The sugar didn't have to filter through any kind of obstacle, so that could be one reason why it moved faster. So in conclusion, because for each of these tests our experimental and mathematical data worked out, it could be said that this would be a good classroom experiment because they would be able to, first of all, they can create their own way to kind of keep the liquids from coming out so fast. We used foil, but you could really use anything you wanted to. And they can measure it themselves to find the rate of flow and then use that rate of flow to answer the question. They don't even have to do the second experimental part as long as they can find the actual rate of flow because they match both mathematically and experimentally.